Okay, this is section 2.1, and we're going to start our whole chapter on reasoning and using logic to make mathematical arguments. So the first thing we're going to talk about is inductive reasoning. That should actually say inductive. Hopefully your notes, I fixed in your notes packet. What is the next figure? So we're going to start looking at just patterns of things to develop our inductive reasoning, which I'll define for you here in a minute. But what is the next figure? So I've got a circle that seems to be common for the three pictures. First one is divided in half and the top part is shaded. Then I divide it in half again and the upper left is shaded. Then it got another line. So I went from one line to two to now three lines, and I seem to keep shading kind of to the left of the lines that I'm making. So my next shape that you would draw, I went from one line to two lines to three to now I need four. And it seems I always was touching this horizontal when I went to shade, so that's where I'm going to shade again. Next, we're going to do a number pattern. So describe this pattern and then write the next three numbers. So you might have to play around a little bit with these numbers. You could think that this is adding, and then when you try and add again, that doesn't quite work. So in order to get from, let me grab my calculator so I can show you. In order to get from 7 to 21, you could do negative 21 and then minus 7. Oh, sorry, negative 7. So it looks like there's 14 in between negative 7 to negative 21, but if I did negative 21 and then subtracted 14 again, I wouldn't get 63, I'd only be at 35. So it's not subtraction that's happening. Some people recognize that if we multiplied by 3, we could get from negative 7 to negative 21. And if I multiplied by 3 again, I would get to negative 63. So this pattern is a times by 3. And then the next three numbers would be negative 189 times 3, negative 567, and then times 3 again, and times 3 again. So negative 5103. So just practicing a couple of different patterns, both shapes and then numbers, trying to figure out what comes next. A conjecture, which we also call a hypothesis, is an unproven statement that is based on observations. Kind of sounds science-ish and less math. I think if I add salt to this drink, it will taste worse or better, depending on your preference, I guess. That is unproven until you give it a try. So your hypothesis is kind of like your guess. Like, I think it might do this if I think my teacher might get annoyed if I talk during class. So those are just hypotheses, they're guesses, and then you usually run an experiment after that to prove it. Inductive reasoning is using your instincts to make an educated guess about what's going to happen. And we are going to make, when you find a pattern like we did up above, and then we're going to write a conjecture. So we're going to write our hypothesis. We're going to write our guess as to what's going to happen. And sometimes we do that in math when we're looking at patterns. Or looking at a different type of problem, we'll notice how it matches some other ones and then say, you know what, I wonder if this will work if I try this. So given 5 points, make a conjecture about the number of ways you can connect different pairs of the points. So I'm going to start you off slow with 1, 2, 3, 4, and then out here is going to be our fifth with a big question mark. We're going to see if we can make enough of an educated prediction as to what will happen. So if I have 1 point, it just looks like that. And there's no way for me to connect it to any other dots because there aren't any, so 0 connections. If I have 2 dots and I connect them, there's only one way to do that. So I can only make 1 connection. If I have 3 dots and I connect them, that's 1, that's 2, that's 3. 3 total connections. 4 dots. So I've got 1, 2, 3, 4, but then I've got 5 and 6. There are 6 different ways to connect those dots. And sometimes in math, we will often start off with a very simple example of our complicated question. So we'll start off real simple and then we'll just build up to it. And instead of drawing out 5 dots and then trying to count me connecting all of them, I just want to see if there's enough of a pattern. Here we added 1. Here we added 2 more. Here we added 3. I am betting based on that pattern that I will add 4 more. So I bet that there are 10 connections. So I'm going to say that you can connect 5 points in 6 plus 4, 10 different ways. So we kind of made our pattern, we were looking at it, and now we're making our guess. I'm going to draw you 5 dots. I got to kind of squeeze it in here because I ran out of paper. 1, 2, 3, 4, 5. So we know that there will be the 5 around the edge. So that's 5, 6, 7, 8, 9, and 10 is my last one. So there are 10 connections for 5 dots. Next says, can you make and test a conjecture about the sum of any 3 consecutive integers? So we need to break this down a little bit. Sum means add. We want to add. 3 consecutive just means in a row. So the numbers 1, 2, 3 will work, but the numbers 5, 10, 15 will not. So they need to be in a row. And then integers, we just don't want any decimals. We can use negatives if you want, but no decimals. So let's just try a few different ones and see what happens. So 3 and 4 and 5. If I add those together, I get 12. Okay. What about if I do a negative? Let's do negative 3 and negative 4 and negative 5. And I would get negative 12. Let's try 10 and 11 and 12. I would get 33. Let's do negative 15 and negative 14 and negative, 13. Negative 15 and negative 14 and negative 13. So negative 42. And we're trying to make a guess about what will the answer be every time instead of me having to write them out or to add them up. And then I started to notice between the middle term and the last one, if I simply multiply by 3 each time, I was getting the answer. So 4 times 3 was 12, and negative 4 times 3 was negative 12, and 11 times 3 was 33, and so on. So I kind of noticed that that's how they're related. I've got a relationship between whatever middle number I pick and the last one. So let's try it without adding. Let's pick really big numbers like 100, 101, and 102. So based on my guess, all I have to do is take the middle one, times it by 3. My answer should be 303. So let's add them up real quick. 100, 101, and 102. 303. So it looks like the sum of any 3 consecutive integers is 3 times the middle integer. And then test it with some other numbers. One number you always want to pick is 0. So let's get maybe negative 1 and 0 and 1. So 0 times 3 would still be 0. And negative 1 plus 0 plus positive 1 is still 0. Just a couple more things. Sometimes, like we were having to list out a bunch of different examples, I don't want to list out all of the possible ways I can add 3 integers together. That would take me a very long time. But to show a conjecture is true, you have to show it's true for every case. So we'd have to go through and prove that this happens all of the time, every time, without fail. That is sometimes very difficult to do. On the opposite, if you want to show that something is false, show that your guess is false, you simply have to find one, and it's called a counterexample. So I'm going to say a conjecture. I say that if you are a sophomore, then you go to every football game. And while that would be tough for me to prove true for every case, I'd have to find every sophomore. I'd have to make sure that every one of them went to the football game. It would be much easier for me to just find one sophomore who doesn't go. So that would be my one counterexample. Another one is if I said if you have a job, then you work every day after school. While it would be tough for me to find every person who has a job at school and see if they work every day after school, it would just be easier for me to find somebody who has a job that doesn't work every day at school. So sometimes doing the one counterexample is much easier. So Joe says that the sum, again that's adding, of two numbers is always greater, bigger, than the larger number. Is that true? So Joe says that the sum of two numbers, let's say 6 plus 7, 13, that answer is always going to be bigger than the largest number. So it looks like it's true right there. Let's do 0 plus 1. 1, oh, it is not bigger. That's a case where it's equal to. Here could be a counterexample. What about, excuse me, what if you did -3 plus -4? This would be -7. And -7 is not bigger than -4. So this could be another counter example. So no, this is not true. And our counter example is 0 plus 1 equals 0. And that is not greater than. So your whole job today is noticing patterns, both numerical and shapes, and then sometimes making a guess as to what you think will happen, maybe testing your guess, whether that's with shapes or numbers, and then learning how to give a counterexample when you're looking to prove something false.